What is a uniform electric field? Good question if you've asked that. And if you haven't, you have to ask it because to understand physics, you have to understand that fact. What is a uniform electric field? Uniform electric field is basically a field that is the same electric field strength throughout the field. In the last video, we introduced what electric field actually is, and we said it's the same as just saying an electric field strength or saying electric field strength. So essentially, no matter where you place a positive charge, if you're in a uniform electric field, the same force will be experienced. What do I mean by this? So to represent a uniform electric field, you have to put two plates, right? One is positive and the other is negative. So this is what we call a plate. A plate is essentially a strip of metal that has a same or that has a particular charge. So if I'm to, let's assume, put a certain voltage across that, put another voltage across that, I've created an electric field between those two different things. So an electric field always moves from positive all the way to negative. That's always the case. So you have you see your lines going from above to below, right? So you see these field lines showcasing how the electric field is actually present in a uniform electric field. So to show that, the lines have to be equally spaced. So by equally spaced, I mean this distance, right? This distance over here, this distance over here has to be the same. They cannot be close at one part, then a further apart at a particular point. That is not going to work. So essentially, this is what we call a uniform electric field. What this implies is if you take a positive charge, place it over here, it's going to fall down with a particular force. Take a positive charge, place it down over here, it's going to fall down with another positive charge. So no matter where you place it, it's going to experience the same force throughout. A non-uniform electric field, however, has a varying electric field throughout. So a stronger field is represented by field lines that are closer to each other. So you can see that they're close to each other at this point. Then a weak uniform field is essentially seen by lines that are equally spaced. Then a strong uniform field is seen by lines that are slightly closer together. So the closer the lines are, and if there's equal spacing, that's a strong uniform electric field. And if the spacing is also the same, but it's more and more apart, we can say that's a weak uniform electric field. And if the lines vary, so they're closer at one point, then they get bigger at another point, we can say that is a non-uniform electric field. Okay, so we can be able to calculate the field strength if given situations where you have a uniform electric field, and you need to be able to do that. So if you have a positive plate at the top, so this is my positive big plate, my negative big plate at the bottom, they're going to be separated by a particular distance, which we're going to call d. So if you have a positive charge that is at this specific point, so this is my little positive charge that is present at that point, as it moves, it does work, right? So it's going to move towards the negative plate at the bottom. So we can say it's doing negative work, right? If you've done gravitational field strength, you now understand what negative work actually is. So the work that is done on the positive charge is given by F is equals to Fe times d. That's the formula for the work done. So you can see that little animation that I draw here. If you're pushing this box, right, work is done on this box as it moves a particular displacement d, right? So work when it is done in electricity, we can also define it as electric potential, right? We're going to talk about electric potential later on, but in AS, you covered electric potential and defined it as the work done per unit charge. So you define it as the work done per unit charge, and that is how you defined V, right? V being the electric potential, so the work done per unit charge was equivalent to V. So now as we go to A2, the work done is VQ. Now you can see that we have VQ being equal to work done, but FD being also equal to work done, so the two can be equated. So in other words, FD can actually be equivalent to VQ. Okay, why am I doing this? We're going to arrive at that in a minute. So we can now divide both sides by Q, right? So if I divide this side by Q, as well as divide that side by Q, right? We can get a simplified version of the equation for the strength of an electric field. So F over Q will be equal to V over D. But we know what F over Q actually is, right? So we know that F over Q is actually electric field, right? Or electric field strength if you would like that. So E is equal to F over Q. So I can remove F over Q and plug in E, right, which is over there. So the electric field strength, or the value of E, which is the electric field in general, can be given by V divided by D, right? We can now easily see that we've created a new equation for electric field strength. Instead of us saying electric field strength is force per unit charge, we can now easily say that electric field strength is the work done or per unit charge divided by the distance. So it's the electric potential divided by a distance d, right? So we're going to see a lot of questions, which we're going to solve a lot of examples for. But you're going to see questions like this, where you're given plus 430 and 0, implying the potential difference V is actually 430, and then the distance is 6.7. So you can easily find E if you have the value of E, if you have the value of V as well as the value for D. So that's essentially what we mean by uniform electric field. It's a field where they're equally spaced and a positive charge experiences a uniform force wherever it's experienced. And for that particular field, we can be able to find the value of the field strength if we know the value of the potential that has been applied for those two plates, as well as we know the separation for those two plates. I hope this was helpful for you. In the next video, we're going to experience what kind of motion do particles experience when they actually travel through this kind of a field. So in the next video, we're going to look at motion of charged particles.